Okay, so we're going to do a surface integral of a scalar field. Let me just remind you that the surface integral of a scalar field is going to be equal to the two-dimensional integral over the parameter domain D, f evaluated at the parameterization, times rs, the magnitude of rs cross rt, ds dt. Okay, so for this, we're going to do number one. So this is number one. Okay, so we just have to fill in all of this stuff here. So first thing, we need to get the parameterization. Well, I've already given you the parameterization and the parameter domain. So this, let me just write the integral up here. So we'll have t going from 0 to pi. We'll just fill this in one piece at a time. T goes from 0 to pi. S goes from 0 to 1. Times f evaluated at the parameterization. So in other words, I have this formula for f. Wherever I see an x, I'm going to put s cosine t. Wherever I see a y, I'm going to put s sine t. Wherever I see a z, I'm going to put an s. So f of x, y, z is just equal to y. So this will be s sine t. Now I need to multiply by the magnitude of the cross product, rs cross rt. Well, rs is equal to cosine t sine t 1, and rt is equal to minus s sine t s cosine t 0. And I will let you do this on your own. rs cross rt is equal to minus s cosine t minus s sine ts. And so this means the magnitude of rs cross rt is going to be, well, s squared. So this is s squared cosine squared plus s squared sine squared plus s squared. So this is 2s squared, or the square root of 2 times s. So this is going to be the square root of 2 times s dt ds. And if you just do this integral, this is equal to 2 times the square root of 2 divided by 3. Okay, so this is the surface integral of a scalar field. Just fill this in. Remember, just like when we were doing line integrals of scalar fields, the orientation doesn't matter. This represents like the mass of an object or something. In that case, orientation doesn't matter, or it could represent the mass of the object or something like that. But in either case, orientation doesn't matter. So when we do the integrals of vector fields below, orientation will matter, but it doesn't matter for this. Okay, let's also do problem number 3. Okay, so now problem number 3, the shape, this region or this surface is a paraboloid that is opening along the x-axis and is opening upward along, or is opening, positively along the x-axis. Okay. All right, so we're just gonna plug in the things that we need to plug in. So I've given you the parameterization and the domain. Well, so I haven't given you the parameterization yet. So we need to figure out the parameterization. So this is a paraboloid, and notice that we are integrating. So the projection of this onto the xz plane, or onto the yz plane, is a circle. Okay, so we should be doing this in cylindrical coordinates. So r of theta r, so the x coordinate is going to be r squared. The y coordinate, this is like the horizontal coordinate, so this is r cosine theta. And the z coordinate, this is like the vertical coordinate, so this is r sine theta. Okay, and this is going to be theta going from 0 to 2 pi, and r is going to go from 0 to 1. Okay, so if you understand why the paraboloid z equals x squared plus y squared from z equals 0 to 1 has a parameterization that it has, this is a very similar parameterization, except it's opening along the x-axis. Okay, so now we need to fill in this stuff. So we need to compute So let's just start writing the integral. The integral, we're going to have r going from 0 to 1. Theta will go from 0 to 2 pi. Okay, the function that we're integrating is z squared. So this is the parameterization. So wherever I see an x, I'm going to put an r squared. Wherever I see a y, I'll put r cosine theta. Wherever I see a z, I'll put an r sine theta. So f is just z squared. So this is going to be r squared sine squared theta. Okay. Now r theta cross r sine. I'll come over here. I'll let you compute this on your own. But r theta cross r is equal to minus r 2r squared cosine theta 2r squared sine theta. And so the magnitude of r theta cross r is equal to r times the square root of 4r squared plus 1. So this is times r, the square root of 4r squared plus 1 dr d theta. Okay, now this is actually, I think this is kind of a tricky integral to do. So the theta integral, first of all, this is theta equals 0 to 2 pi. Let me write that on the outside. The theta is a constant with respect to r, so I can write it like this. And now the r integral is going to be r equals 0 to 1 r cubed, the square root of 4r squared plus 1 dr d theta. Now this one, you're going to do u substitution, okay? And it's going to look like it's going to look like it's not going to work out, but it will. So u is equal to 4r squared plus 1. Du is equal to 8r dr. And so let me just look at the r integral. So the r integral then is going to be the integral from u equals 0 to 5. Well, having trouble writing a 5. I'm just going to write what this is with the u stuff, and you can figure this out. So this is going to be r squared times u to the 1/2 du over 8. So obviously this is a problem because we have the r squared there, but we need everything in terms of u. So we come over here, now we have r squared. We can solve for r squared in terms of u. This says that r squared is equal to u minus 1 over 4. And so now this is going to be 1 over 8 times 4 times the integral from u equals 0 to 5, u minus 1 u to the 1/2 du. And you can compute this, and you can come up here, plug it into this, and get that the answer is 1 over 120 times 25 times the square root of 5 plus 1. Okay, so that was kind of tricky because we had to do this, we had to do the right r squared in terms of u here. Okay. Anyways, so that is it for these two problems.